Okay, greetings everybody. We're back for another edition of Stat 5114. Let me push this back just a little bit. We're also going to have a static recording of this class up. So if you come in late or whenever, this is just our demo run. So apologies on the late notice here. We'll be trying to do this every Monday, Wednesday, Friday at 3:30 to 5 o'clock. We'll be following up at about 4:20, so 3:30 plus 50 minutes. We'll do our class, and then we'll pour it over to maybe a Q&A session via Zoom. So we have three media devices. So the static camera is still going to persist with high-res video, the live session, and you can interact on chat. Let me just introduce, we have Sierra Marquez here. So she has been out fighting and scrapping, so she damaged her knee out there, so she's going to be rolling around and trying to convey questions. So if you have questions, you want to badger me about my typos that I always make, maybe we can play a game and see how long it takes me to catch them. So since I don't have the full audience, but basically interact with her. She's going to convey questions, and then we'll move to Zoom. We're just checking some technicalities out real quick.
It says chat is disabled.
Chat is disabled. Okay. Sorry, guys. Sierra is going to try to figure this out, and I'm going to start teaching. So she's looking at it real quick, and we'll see if we can find where the button is. Keep going, I got you. Well, she begins with that. I'm going to just bring us back around to our old example. This one that's been our friend for quite a while. And today, everything's going to look a little bit more complicated because I'm going to talk about joint estimation. So sigma squared is V, is what we called it last time. And we're going to have n IID observations. So same basic setup, and we're going to try to co-estimate this. We've already seen one of the answers. So a mom estimate. So method of moments estimate was mu hat mom. This one's pretty uncontroversial, x bar. And sigma hat squared V was equal to sum of the xi's minus x bar squared over n. And there was another mom estimator that we came up with. So we also matched moments to come up with this answer. So also, mu hat mom is equal to x bar, and sigma hat mom, I'm going to call this 2 and this one 1. So mom 1, mom 2. Or this is mom 1 right here. So v mom 2 was equal to sum of the xi's minus x bar squared over n minus 1. So we had that familiar creature as well. And I'll remind you what we did is this one we matched expectation of x is equal to mu. And we also matched so we'll say this thing, this is mu, and we matched using this right here. And we also matched the expectation of x squared to the empirical second moment. So this is how we did this. And in this method, we matched expectation of x, mu, to some of the xi's over n, same old thing. And we also matched expectation of s squared. I'll remind you what s squared is. It's just this thing, n minus 1, and we directly matched it to sigma squared. So we said that this was approximately some of the xi's minus mu squared over n minus 1. And so for both of our methods, for these answers, both of them, we ended up saying the center's like x bar. That's a pretty reasonable thing to do. We like that for a number of reasons. We like that because of the central limit theorem, probably one of the more important reasons, but this has all kinds of nice properties. And estimators like it, have nice properties. The variance, there's some choices that can be made here from the MOM technique. Now, if you're like me, you like choices. So I like to have different knobs and I like to understand what they mean when I make these choices. For the MOM estimation technique, method of moments, I can't say I actually understand what the choices mean to match these particular moments. So it's a little bit artificial for me. So there's choices here, but I don't have any guidance on those choices and what to do. One nice thing, I guess, because of in the maximum likelihood estimate technique, there really aren't any choices. You just write down your likelihood. If you know what your model is, you see data, you plug it into that sampling distribution equation, and then you treat it as a function of all the unknown parameters. You maximize over those. You solve that system by taking the first partials, setting them all equal to 0. If you have n equations, you'll have, or if you have n unknowns, you'll have n partial derivatives that you'll be setting equal to 0 in solving a system of n unknowns with n equations. So we know how to do that. So no choice right here. In Bayes, we kind of said is similar to maximum likelihood, except it has the prior distribution. This extra penalty. I want to convey today, they're actually quite a bit different. So while they're both functions of the unknown parameters, in this example, mu and v, the Bayesian solution is an actual measure. It's a probability distribution, and the maximum likelihood estimator is just a function. And I want to dwell on this because it's extremely important. A lot of people brush these things under the rug at first, but they are important. And they'll really yank around things like maps, how we treat those spaces. So I want to spend a little bit of time talking about the difference between these things. First, I want to convey maybe a useful prior. So our likelihood function is just this, likelihood of mu and v, however you want to parameterize this. Just keep reminding you it's equal to sigma squared. Given all of the data, is proportional to this product. If I use v to parameterize it, I would do it like this. E to the minus 1/2 xi minus mu squared over v. So that's my likelihood function, and it's a function of mu and v, and I've denoted that by writing those over to the left-hand side of the bar. Okay, so nothing new up my sleeve. But I ended up talking about some priors last time, and I think I actually made an error when I claimed what the map estimator would be under those priors. So I want to analyze that case really carefully. And then maybe we can understand some differences between Bayesian analysis and maximum likelihood. So again, the Bayesian analysis is a full distribution. Likelihood functions, if you maximize them, it's just a point we're talking about. So with the Bayesian inference comes lots of flexibility, so we have to understand exactly what we're doing with that flexibility. We don't want to use it just blindly. So likelihood function is that. In the prior, I ended up suggesting from last time was this. And I'll write it out just a little bit differently. So the prior on mu in V. Okay, what I ended up advocating was this being proportional to some flat function, and I arbitrarily wrote that down as 1. So this looks like this, flat. That's 1 right here, and this is mu. That's what my prior distribution looks like. You'll forgive me for saying the word distribution, because this goes out from negative infinity to infinity, and that's pretty big. So if you try to integrate over this thing, it will blow up in your face. You wouldn't actually be able to normalize this distribution. So because you can't normalize it, we say it's an improper distribution. Now, what I'd like to convey to you right away about Bayes is this is, in some sense, some sort of penalized likelihood thing. So we're thinking about this as a penalty function, but it's also inducing a random measure. So it's flipping the conditionals around, and that's what Bayes' theorem does. So this isn't a distribution, but we don't do inference off of the prior. We do inference off of the posterior. So the important thing to note is that our posterior distributions are actual distributions, but our priors need not be that. If you want to get really mathematical about this, we would start talking about this in terms of limits of proper priors, prior distributions that don't have infinite mass off in the tails. So what I mean by that is that prior distributions that integrate and we can normalize them. Okay. So this is a limit of a normal proper prior where the variance is going up to infinity. That's a lot to chew on for right now, so let's not worry about it. But what I will say is this is shift invariant. So what I want us to take a moment to do is kind of appreciate that this parameter right here has an actual interpretation to us. And that's a very critical part of doing inference. And so it's not just a bunch of Greek letters, but it's how they interact in the original model. And so what I'll notice is that this mu right here is a shift parameter. So what I mean is in the sampling distribution, f of x, given mu, and v, it looks like this, where this is centered at mu, and this is some function of v. It's actually sigma, so square root of v is the distance from here to the first inflection, or the inflection point. So all very interesting. So that's a shift parameter, meaning if I move mu linearly 5 units, this whole distribution moves 5 units. So shift parameter. It operates linearly. This distribution is going to make no claims in a shift sense about what mu is. So that's what this says right here. So not specifying. The shift. So I'm not coming in with prior knowledge about what that shift is. So let me show you what it means to really be shift invariant. So consider 2 random variables, x and y. We'll just say these are random variables. And I might do something with these. I might add some shift to both of them. So this is an actual shift. Shift. Same shift that I add to both of them. And I might ask the question, is that if I add these 2 things together, and maybe we'll do it this way. Let's say subtract. Since we're used to thinking about shift parameters, I subtract it, and I need that incremental value to put it back in the same location. So let's subtract. Pretty arbitrary. And then let's just subtract these two things from each other. Consider this. X minus C minus Y minus C. You might ask, why did I do that? Right here. This is the shift operator. So if I shift these two random things by the same increment, and then I look at the shifted difference between them, I might want to make a statement, a mathematical statement about what distribution X and Y need to follow so that I can't tell that I just did that versus just comparing X minus Y. So what distribution could I impose on these right here so that the shifted distributions, and I consider the original operator, has exactly the same properties. And so this thing right here is invariant, i.e. the distribution, these differences right here are invariant given the original distribution for X and Y is flat. So let me just say that in words. For these two things, 1 and 2, to have the same distributions, the same properties, X and Y must be flat. That might not seem mathematical to you when I say the word flat. Here's what it means graphically. Here's what I mean notationally. So that's shift invariant. Basically, this distribution, if I slide it back and forth, I can't tell. Shift invariance. Let me show you scale invariance real quick. Very similar. So I'm kind of giving you a geometric sort of argument for the prior that I'm going to use, but there's lots of arguments for these priors. So this is scale invariant. Let's just write down my prior distribution on V is proportional to 1 over V. This is a scale invariant distribution. This is shift invariant. Adding and subtracting is a very intuitive process for human beings, and I believe that's because we count on our fingers. We can see things and we can count them. Let's think about what this means. Under the same operation, I want to make sure that when I scale this thing, it's exactly the same. And so what I mean by that is if I take C over some random variable that's coming from this, divided by, same operator, C divided by Y has the same properties as X over Y. I can't tell that I did it. So that's what scale invariance means. And so these things cancel. Same sort of argument that I just used before for shift invariance. I'm not going to dwell on that, and I'm not going to ask you about it on your test, but I just want to argue that maybe these have intuitive rationales. There's other mathematical reasons for coming up with these priors. They're optimal in some settings. So when I have more than one reason for using something, I get really comfortable with it. Anybody that's taken a Bayesian class probably has a dozen or so reasons to why they might use those priors. There might be other priors that you use as well. Okay, I want to show you something before we begin with the Bayesian analysis and the likelihood-based thing. I want to just show you that these priors pi mu and pi v proportional to 1 over v, and I'll use them for joint inference by multiplying them into each other. That's not the only game in town. So what I'm saying is only marginally true. And jointly, it's not quite true. These are not joint Jeffreys priors. And I'll show you some of the things that I mean and why you might want an actual Bayesian class and understand these priors a little bit more. I do understand about 10 of you have had Bayesian classes before. So this is going to be a little bit more meaningful to you. So pi mu and pi v are Jeffreys priors. I'm not going to tell you what that means. Explicitly, but they have some special mathematical properties that marginally these priors are transformation invariant, meaning that if two different experimenters are working with these priors under this framework, they parameterize it like this, or they pick some other arbitrary parameterization, they'll come up with the same inferences. So this is only true marginally. And jointly, these are not Jeffreys. Note, these are not joint Jeffreys. The take-home point that I'm going to end with is what scale you operate on can change your inferences, and you need to be aware of it. And it's virtually true for any class of inference, but the Bayesian's pretty upfront about this. And so you might think about what sort of prior might I need so that jointly everything is invariant to transformation. That is, if another experimenter is using that same methodology that I'm using, we'll come up with the same inferences. I think that's important. Okay, so lots of notes about things. To choosing my prior on sigma being proportional to 1 over sigma, and also equivalent to choosing under this transform. I'm just going to write this down. G of v, so this is going to be a transform function, is equal to 1 over v. This is just a transform. I'm going to call that something. I'm going to call it phi. I'll walk you through these calculations in just one moment. This is proportional to 1 over phi. So I want to say that at least marginally, these all mean the same thing. Let me show you what I mean by that. So I'm going to write these up here. We're building up to a point. I'll make it in a couple moments. Okay, we've got this. Pi v is proportional to 1 over v. You could probably rationalize that when I flipped v over and I called it phi, that's also a scaling parameter. It's just, instead of dividing, I'm multiplying by the inverse. And so that should have that same sort of invariance property. And all of these priors that I've written down, they're scale invariant. That is, if I divide them by something after multiplying it by something, that multiplication washes. But I'll say, if I'm specific about what pi means right here, this is for a random variable v. I have this distribution 1 over V. I'll point out this also does not integrate over this range. V is greater than 0, so it's positive. It's variance, positive. Sigma is positive, V is positive. So sigma is equal to square root of V. That's my transform. So this is my new value right here. So this is a transformation. Or I'm going to say phi is equal to 1 over V. So these are my transforms that I want to consider. I've asked you throughout chapter 5, pay special attention to transformation functions, because there's a lot of insight that can be gleaned out of them. And when we transform our data or transform random variables, I think we need to be aware of what we're doing. And if we're not, I don't know, I think a lot of things can go wrong. So I know this might be complicated, but it's extremely important for why we parameterize things the way that we do. I will say this thing right here, if I want the probability distribution on pi, let me write pi sigma. What I do is I end up saying this is going to be pi for V. I plug in whatever name for V is right here, and then I take whatever that transform function is, and I make it a function of sigma. I take the Jacobian over it. So this is how I transform a random variable. That's how I've always done it, how I'll continue to do it. So what's V? V right here is equal to sigma squared. I don't need to be too careful about the positive, negative signs on all of this. I am creating a bijection because I'm only considering the positive side. So this right here is going to be, when I see a V in my original distribution, I plug in a sigma squared. So V is equal to sigma squared right here. So what that means is I just take my original distribution right here for V, 1 over V, and when I see the V, I plug in sigma squared. And that's that. And then I take this derivative right here. So I put this in terms of sigma squared, this same function, sigma squared d sigma right here, and I know how to do this. This is equal to 1 over sigma squared. This is going to be 2 sigma right here. I want to remind you, this thing right here, when we wrote it down, it was up to proportionality because it did not integrate. And so this is really a proportional sign down here. And so this is 2 over sigma, which is proportional to 1 over sigma. This has the same shape as that. Okay, so what we just showed is that this is equivalent to pi sigma 1 over sigma. It's proportional to 1 over sigma. Let's just do this one more time and do it for this one. So if I want the equivalent prior distribution on phi, so I'll just put phi right there. This is going to be equal to pi v on V, but I'm going to change the name of it to whatever it is in terms of phi, and then I'm going to multiply by my derivative with respect to phi. So that's the stretch factor in a transformation that comes up. And so what do I plug in right here? Well, this was 1 over V, but every time I see V, I write down V is equal to 1 over phi. So I rewrite this in terms of phi. So 1 over phi, if you will. That's another way of writing down phi. This is going to be times d 1 over phi, same function with respect to phi. So this is going to be minus 1 over phi squared. Absolute value gets rid of that right here. This is really the chain rule in disguise, if you will, and this is just 1 over phi. So it turns out this is also equivalent to pi phi, proportional to phi. They're all equivalent priors. They're the same measures on transformed bits of spaces. So Bayesians are working with probability distributions. All the rules that we know for probability distributions are always true. Okay, so there's a lot to take in. Let's go simpler and start looking at the maximum likelihood estimate for what we just wrote down, and then I want to compare it to 3 different possible Bayesian inferences for maximizing the posterior. And then I'm going to ask you, ultimately, you need to be more careful when you do everything. And then I'll tell you some good take-home points. This is supposed to provoke you to think there's more to Bayes than just penalized likelihood. Bayesians are working in measure spaces, and they come with special properties. Effectively, we have to do this bit in our transformation, and that changes things, restretches the space. Okay, let's just back up. I'm going to use everything we said right here in a couple minutes. But before we do that, let's just maximize the likelihood function. So joint maximum likelihood. Then we'll compare to Bayesian analysis, and at least you'll be thinking, when I operate on different scales, I actually do mean different things. I need to be aware of that. Okay, so my likelihood function is this. I'll write it down in terms of V. And then I'll say a few things about it. So this is proportional to product, if you will. I'll write it down in terms of V. 1 over V to the 1/2, e to the minus 1/2, xi minus mu squared over V. Allergies. Everybody's safe. Okay, this thing is just 1 over V n over 2, e to the minus 1/2, sum xi's minus mu squared over V. My likelihood function. I don't really feel like maximizing that. I'm much more inclined to maximize the logarithm of that. It'll make everything a lot simpler. Same answers in the long run, one is easier. So on a computer, I would also work with a log function of this. So let's just look at the maximum. The arg maximizer of the log likelihood function. Said I wasn't going to do this explicitly last time, but I think there's a lot to say about it with respect to the Bayesian analysis. So I'm going to arg maximize this over mu and V, and I'm going to call that mu V hats. So it's going to be that joint set as I maximize over these things. Okay, so a little bit of calculus, and then we'll come back to the Bayesian thing and see how maps operate with respect to MLEs. You'll notice there's quite a bit of differences. Okay, so this thing is just going to be, I'll start with mu, and then I'll work on V. And I'll take a logarithm in there, if you will. Let's see. Log likelihood. Log likelihood. Okay, so this is d mu. going to plug everything in. I'm going to do this rather quickly. So this is going to look like this. Minus n over 2 log v minus 1/2 sum of the xi's minus mu squared over v. Okay, all I did is just slide the logarithm through this. I inverted it. I pulled down that negative sign in the inverse. I producted everything up. And so I did everything in one big step right there. So we've done that calculation so many times, shouldn't irk anybody. Okay, let's take our derivative and slide it through. No mu's there, how convenient. So that's 0 minus, and I've got some mu's in here that I want to work with. Lots of different ways I could do this. Maybe the chain rule is the simplest thing to do. So I'll just say minus 1/2 sum 2 times xi minus mu over v. And then I've got the minus that I need to worry about. So that was the chain rule right here. So all I did is I multiplied this by -1 right here. Taking the derivative with respect to minus mu, flip that sign, if you will. So almost done in all of this. A lot of nice cancellation. We really didn't need that right there. But now I can ask the question of how do I want to infer mu? So this is the MLE technique. So the MLE happens when I take this equation and I set it equal to 0. As soon as I do that, I need to throw a hat on top of that. So this is mu hat MLE. You'll notice the v cancels on the 0 side, so that doesn't become important. And so this is just sum of the xi's is going to be minus n mu hat MLE is equal to 0. So this says mu hat MLE is equal to x bar, sum of the xi's over n. So very convenient. Everything just worked out real nicely right there. Okay, let's get rid of that. This is the more interesting one. So there's always this contention of how you estimate variances. Kind of know what the minimal sufficient statistic is. We'll see it appear in here. But what you do with it, a lot of different people do different things with it, and we're going to have to provoke some questions out of this lecture. That's what this lecture is supposed to do. So you should be leaving this lecture and going, lots to think about. So, and that's what being a statistician is all about. So, take my derivative with respect to v. I arbitrarily parameterized it in terms of v. And now I'm going to take my logarithm of everything. Here's my log function. I'd already done that. So minus n over 2 log v minus 1/2 sum of the xi's minus mu squared over v. I'll point out something real quickly in this calculation is that I can't untangle that v from here. So I like that thing. If I didn't know what mu was, I'd plug in mu hat for my other equation. I'd have x bar sitting right there. I'll never be able to disentangle everything. We'll see that again in just a moment, but you'll recognize that as the minimal sufficient statistic, depending on if you know mu or if you don't know mu. So you're always going to use this function right here, and you're either going to plug in for mu, x bar, or not. Okay, so derivatives. Got two functions that I need to work through. So this is going to be minus n over 2, 1 over b. derivative with respect to v, but log v is 1 over v minus 1/2. This is all a constant with respect to v, but that one's not. So this is going to be v inverse. I'll do the little exponential rule that I know. So bring down the -1 in front of there, plus, and then decrement my index. I'll do that all in my head. So this is v squared down here. And I switch the sign right there. Okay, now for my magic maximum likelihood technique, I'm maximizing a function. So I'm going to set this equal to 0. As soon as I do that, I better throw some hats on stuff. Plug that in for x bar, that was mu hat. Okay, so basic calculation that we see in the book. And we get some nice cancellations. So one of those is gone with that right here. Those 2's are gone. So what we end up getting is that v hat is equal to sum of the xi's minus x bar squared divided by n. That's what we promised last time. So I'll remind us, we had found this. And so that's our joint maximum. And we would need to verify this if your teacher was being really nitpicky and say, show me real quickly that there isn't something on the boundary. I already know asymptotically what this function looks like. Tails come down on it, things like that. So I know that I don't have to chase off into infinity to find the max anywhere. I'm just familiar with looking at this function. And I would do the second derivative test and verify that that's actually a max and not a min or something like that. But I know what this function looks like. Of course, it's a maximum. But you're supposed to check those things. The book urges you to do it. And for more general problems, you would probably get worried if your maximums were on the boundary. And I leave that as a hint for you to ponder for a moment. That if you were using the map in that odds ratio problem, boundaries cause problems. So I know I encouraged you to do it, but some of you took the bait. So I think there'll be a good learning lesson there. We'll come back next time. We'll talk about it. So here's my MLE. So that's the MLE. These things right here. And this is the joint MLE. That's kind of cool. Okay. I've been saying Bayes is kind of like doing likelihood-based analyses, but there's a fundamental difference that one of them is a measure and one of them is just a function. So before saying anything about the Bayesian analysis, let me just ask you this. If let me give this a title. MLEs, maximum likelihood estimators, are transformation invariant. Now, I don't mean that's necessarily a great thing. Of course, it makes all my math easier. But there are repercussions to this. You might come away from this lecture and go, I don't want to do that Bayesian thing because I need to think about stuff. But remember, thinking about stuff is what statisticians actually do, and we have reasons for our choices. Well, let's just do an example. And I'll see what we mean right here, and later on we can prove this. So proof next time. I'll give you a construction where you'll kind of know that this is true, and you'll know what it means. Example. Let's say I have my likelihood function, and I was maximizing V. So let's just say this is the likelihood function with respect to b. I'm gonna say you know mu, just to make this easy. It's a function of b. So this is starting to peak. Doesn't always peak. It can flex in weird ways. Looks like an inverse gamma function. So in disguise, I know a lot about those, just like beta functions. Okay, so this right here is v hat MLE. And I'm going to give this a number. I'm going to say it's 5. So I just made that up. But let's say I found it. So this is actual data. Actual. And I plugged it in and I got this curve and I maximized it and I got this number 5. So I looked at this equation. 1 over v to the n over 2, e to the minus sum of the xi's minus mu squared, my half in there, plug in v right here. So I look at this function, I plug in all of my data, and I also have to plug in mu. Okay. Everything I'm saying that's going to happen happens in the joint inference and in the marginal inference. Just make it simpler. So I'll just write down this function. It's actually proportional to, doesn't change where the maximum is if I multiply by any number. Likelihoods are self-relative. This is the actual maximization, and that's the thing that maximizes it. Okay, so if I look at this function right here, I'm going to write it just a little bit differently. E to the minus 1/2 sum of the xi's minus mu squared. You'll appreciate this is just a number right here. This is a function of v right here. We know when this function maxes. So this function right here is drawn here. So I've plugged these in. Fixed. So this whole thing is fixed. And my maximization happens right here when it's equal to 5. So I'm just gonna write something obvious. This is equal to max is 1 over 5 n over 2 e to the minus 1/2 sum of the xi's minus mu squared over 5. Okay, this is supposed to look like kindergarten right here. I'm just plugging in numbers. Here's the big revelation. Let's say I transform real quickly. We'll butter this up with a proof next time, but I think it's pretty easy to see. Just to know how functions operate. So let's consider this transformation. Phi is equal to 1 over v. Now I'm going to give you some names for this. This right here is called the variance. You know that. There's other statisticians in the world that like to play around with that. It's called a precision. I'm going to argue to you right now. One is as arbitrary as the other. For obvious reasons, I think. I don't think I could come up with a good reason to say what we think invariance because it makes sense to. So there's mathematical reasons we do it. And just as arbitrarily, I can invert the thing and talk about it on that scale. So if I have a lot of variability in something, I'm not very precise. My precision number is small. And if I have very little variance, I'm pretty sure about things. Tight variance, this number gets big when variance gets small. So precision is high. Okay, so different interpretation, different word, same construct. Not too much difference. I will warn you in a moment, we'll have to be a little bit more be a little bit more careful about this. So variance precision right here. So the question is what's arg max over phi of this new likelihood function? Just be perfectly redundant about the notation, mu and x are known. So this is going to be some number. It's going to be the MLE. So some people think on different parameterization scales, arbitrary stuff you're allowed to think about as arbitrary as you want. So some other experimenter likes to play around with that. What is that? Say they knew this. Well, here's the likelihood function. So first, what's the likelihood? This thing is just 1 over, and I'll show you my magic trick. Let's just parameterize this in terms of v first. Shouldn't change n over 2 e to the minus 1/2 xi mu squared. I goes from 1 to n. And this was 1 over v. I just wrote it a little bit differently. But every time I see v, I just switch to something else. So if I see v, that's 1 over phi. So 1 over v is phi. And 1 over v is phi. Very simple. Same functions, just written down slightly differently. So if I want to maximize this thing right here, it looks like something, it looks like a gamma form, if you will, versus an inverse gamma form. You can actually just look at the answer over here. This is a function of these things over here. So this is some sort of a penalty in here that's damping the whole function. This is doing something else. So I know what I need this to be. I need this to be 1 over 5. I need this thing to be 1 over 5. That was the thing that maximized this function. So I need that argument to look like this for it to be maximum. I'm plugging in the same exact stuff, so I know where it's maximized. And so that means that this thing itself is 0.2. So it looks like kindergarten because it kind of is. And there's a proof. And this happens no matter what the transformation is. So if it's 1-to-1, if it's a bijection, if it's not a bijection, you can just plug and chug and recycle your NLEs. So this thing right here is 0.2, 1 over 5. So here's a fact. MLEs are transformation invariant. Let me show you what I mean by this. So say theta, let's call it theta. So this is just arbitrary parameterization. I don't have any example in mind, but if you need an example, go back to this one. Let's say theta is equal to the arg maximizer, let's call it theta hat, the arg maximizer of this likelihood function. Just an arbitrary function, not a random measure. It will change quite a bit. You want to consider the transform. G theta. Just some function. It doesn't need to be a probability distribution. Just something that I plug this into. And I'm going to call this psi. Okay, so So that's my new variable. Then the argmax for my new parameterization is going to be equal to G theta hat, which will be psi hat. So it's equal to that. That's what it is. I can just take my old maximization and plug it into that function and I'm done. We'll prove that that's true regardless of what G is. Be careful, Bayes is totally different. So, and I've seen this mistake made a lot. I'd like people to think about which transform functions they're working on. But I want to go back to our parameterization that we introduced before, sigma, phi, and v, and show you that under those three priors, things will change on you. The reason why is because everything we did is not joint Jeffreys or joint transformation invariant. And there are ways to do this, and this will motivate you to think a little bit more about maybe taking a Bayesian class and not just likelihood times prior, but there's mathematical impacts to all of your decision making. And I think that's good. You should be thinking about your parameterizations, why you picked them, what properties they have. But here's back to Bayes. Sierra, are we doing okay with questions?
I still can't figure out the chat.
Oh.
I think we have to log off to do it.
Gotcha.
But I am on Zoom right now, so if anyone wants to join Zoom and have a question.
Oh, very good. Okay, so Sierra just said she needs to disconnect YouTube Live. We won't do that right now to get the chat enabled. Figure that out for next time. There's some toggle in there I think you need to preset. But she did go to the Zoom link that I posted in the email update. So she's got that going right now so we can experiment with that. And if you want to join Sierra, she'll entertain your chat questions there on Zoom. Okay, Bayes. This is all in the book also right here. But I want to give you more to think about than what's in the book. So let's consider PV, or our prior. These things. Let's just work with this problem. And I had said something incorrectly last time about what the map would be in this case. So let's look at it. So our joint posterior on these two parameters just looks like this. Likelihood times prior. So same likelihood function, 1 over v n over 2. E to the minus 1/2 xi minus mu squared over v, sum over all of that. And my prior is 1 over v. Now I've argued maybe this is a good prior. Well, let's see how it does. We're gonna explain a few things in Bayes under these priors, but I just want to give you the sense you should be thinking about lots of things when you do analyses. So this is just the same function we saw before, but I've appended this. We're going to think about, does it change our answers very much? It does a little bit. So this is 1 over v n over 2 plus 1. I'll combine that to a plus 2 right there. So I'm really adding 1. E to the minus 1/2, sum of the xi's minus mu squared over v. Now let's maximize that. You can already see we're going to come up with a different answer. So let's just maximize this, the map estimator. So maximum A-Posteriori. Estimator. It's called a map. Let me give you another name for it. Posterior mode. So this is the posterior. We're going to maximize that thing. Looks and feels a bit like an MLE. Doesn't share the same property that MLEs are benefited by, perhaps, maybe. Makes everything simpler. But I think if you work in measure spaces, be careful. So posterior mode. It's just going to look like this. I'm going to not do this, but I'm going to take a logarithm of it because it'll make the math easier. And so what I want to do is I want to look at the log of this function, 1 over v n plus 2 over 2 e to the minus 1/2 sum of the xi's minus mu squared over v. Okay, I'm going to take the logarithm of it, and then I'm going to take some derivatives. So this is going to look like n plus 2 over 2 log, I'll say v, throw the negative sign right there, minus 1/2 sum xi's minus mu squared over v. So let's take a few derivatives. The one including mu that has to do with mu, that one doesn't change. Remember, the thing that we just changed right here is this. So if you'll allow me, d mu log pi mu v given x. And then I'm going to set this thing equal to 0. And I'm going to solve for mu is equal to mu hat. And I'm going to write down map 1. This is going to figure that mu map 1 is equal to x bar. That's the exact same math that we did before. If we do that, and so when I take my derivative over mu, this goes to 0, and this is gone. Okay. That's going to be true everywhere. Very bad insight to just show how different fields overlap when we estimate mu. We overlap for a lot of reasons that isn't shared by doing estimation on the variance. But let's take our derivative with respect to the variance, and we'll see what our answer is. Remember, this didn't exist before. So dv respect to the variance, n plus 2 over 2 log v minus 1/2 sum of the squares. Here's divided by v is equal to this. N plus 2 over 2, 1 over v minus 1/2 sum of the xi's minus mu squared over v squared, change the sign. So same calculation as before. So what does that mean when I set it all equal to 0? So I'm going to plug in my mu hat map equal to x bar right here. I'll set that equal to 0. Plug some hats on here. That's not equal anymore. I can get some cancellation in here on different things, and I wind up with v hat map 1, if you will, is going to be sum of the xi's minus x bar when I plug in mu hat divided by n plus 2. I personally love this, that I got some difference from my old answer. So everything's different right there. Let's just look at a couple other things. Let's consider this. Consider this new parameterization. Sigma is equal to square root of E. This is my new transform. Our equivalent prior for this, we had already figured this out before we did everything. It's this. So equivalent prior, same prior as before. I wrote down under this analysis, pi v is proportional to 1 over b. This means exactly the same thing. So if you argue in favor of that prior, you've also argued in favor of this one. This is a bijection. So this means that in different notation. Still has that same scale interpretation that I had before, and it's benefited by this same scale invariance. So let's just write down our log. I'll say 1 over sigma times my likelihood function. So this is my prior. This is my likelihood. Usually multiply them together in the other way. This might be the first time I've ever done this. Doesn't make any difference. So this is going to be sigma producted up, e to the minus 1/2 sum xi's minus mu squared over sigma squared. Same likelihood function. This is going to look like this. So this is sigma x raised to the n, so this is sigma to the minus n. So sigma to the minus n, and then I've got this other one in here. So that's producting these together and that one times e, take the logarithm real quick, minus 1/2 sum dxi's minus mu squared over sigma squared. Not too surprising what will happen right here. Sigma to the, I'll say this is logarithm, sigma, need to clear it, minus n plus 1, 1 over sigma after I take my derivative through, minus 1/2 sum of the xi's minus mu squared, and I've got 2 sigmas to tend with, and so I need to take the derivative of that. So sigma to the minus 2, pull that down, 2 right here, and this is sigma 3. So I did a lot of calculations all at once, mostly in my head, because this was the same thing we did before. Same sort of thing, I just did all the derivatives for you and took the logarithm in one step. That confuses you? Rewind a little bit. You'll see exactly what I did a moment ago. And so when I solve for this and I set it equal to 0, that ends up putting a hat on everything. We'll see some cancellation in all of this. So this is a 2 right there. And twos cancel very nicely right there, all by themselves. I didn't have a 2 in here. And so this is going to be sigma hat. This is going to be for the map estimator, is equal to, this is a squared right here, xi minus, once I plug in x bar into all of this, I'm going to divide by n plus 1. I want to take that square root over the top. That's my map. Let's do it just one more time. I want to point out, maps are kind of different. This is divided by n plus 1. This was n plus 2. We've looked at n minus 1. We've seen n pop up in different inferences. If we do this again under a different parameterization, I usually do this, I get a slightly different answer. This tells us we need to be more thoughtful. I will point out, this is the minimal sufficient statistic. If I didn't know mu, they pop up in all the answers that we are deriving. So lots of different derivation techniques, kind of similar answers, but now we're seeing differences occur. Question is which one do we want and why? So one more time. So let's look at this. I'll remind you, v is equal to 1 over phi. So that's the precision parameter. So let's just do this analysis right here. The likelihood is just going to be phi to the n over 2. This is a plus sign. E to the minus phi over 2, sum of the xi's minus mu squared. I've already divided. My prior is this. So my posterior function looks like this. Phi to the n over 2 minus 1. New penalty that just appeared. That was kind of fun. E to the minus phi over 2, sum of the xi's squared. We could do all the math. Over this derivative is pretty easy, but since we've been doing a few things in our head, I'll just do the whole thing in my head and you can verify this. Map. This is x bar. This bit doesn't change anything. I take my derivatives over mu. And phi in all of this. So we'll just end up writing down this whole thing, if you will. This is minus 2 over there. The map estimator is a little bit funny in all of this. So this is going to be n minus 2 over sum of the xi's minus mu. Oops, minus x bar squared. This is inverted because I'm dealing with the inverse thing. So, but this is different right here. So, kind of interesting. Let me just back up and rewind real quickly and say what happens with the MLE. With respect the MLE, we have these three results. V hat MLE. We're going to have sigma hat MLE. And we're going to have phi hat MLE. Solve this one. This is sum of the xi's minus x bar. This is with mu hat MLE being equal to x bar. And this is true for all of them. We all agree there. Divided by n. Sigma hat MLE. MLEs are transform invariant. So all I have to do is do the transformation to this thing directly. Square root sigma xi minus x bar squared over n. Right here. And phi is going to be 1 this is just going to be inverted. N over sum of the xi's minus x bar squared. It's the inverse of it. The map, however, changes depending on if we transform it. And the reason that happens is because of the Jacobian term. So remember that when we do a transformation, I'll just say this, a posterior distribution in general is likelihood times prior. So when I transform, let me write down this is proportional to. There's just these two bits. When I transform this is just plug and chug. It's likelihood function, it's not a measure. And so you just transform directly. But this bit right here, this stretches the space. So if I end up magnifying it by multiplying by something or exponentiating with it, I'm changing the way volume adds up in space. So that area in the space is changing because it's getting stretched when I do a transformation. And this has that Jacobian term built into it. And so we're really thinking about how things are changing probabilistically. I consider this a great benefit to being a Bayesian. It keeps me coherent as I move through scales and I understand how I've changed my answers. So I will say that when you're doing analyses and things change because of seemingly arbitrary choices, or using sigma, for instance, maybe you've changed your probabilistic view of things. Ultimately, you've changed how you think about that space altogether. I do want to say, be careful with the maps. So maps can be a really good answer, or they can be really frustrating answers depending on where they occur. Things like variances, they don't have these nice properties where we all just agree on which estimator to use. So that begs the question of how do we even know? I'll also point out, before I say this, and these little penalty terms, n-2, n-1, n+2, I'd probably come up with a way for an n+1 in there, probably come up with lots of penalties. They are all pretty similar to each other. And so chances are if we were doing these sort of inferences and n was like 31, I mean that facetiously, but if you're like 31, we probably wouldn't quibble too much about it. But for other problems, it might be a bigger deal. So we need to answer the question as to what did all this mean? So what did it mean to use the map in the first place? What did all this stuff yield to us? So it's a process for coming up with answers, but now we need to be able to compare these answers on equal playing fields. So we kind of looked at this a little bit in your simulation homework. I'm still reading through it. I think there's lots of valuable learning lessons there. So we'll be talking about that soon after I make myself a list of take-home points. I'm going to grade things kind of in the manner of 3 piles. This looks really good. You've been thoughtful. Technically, you've satisfied all the things that I've asked you, and you've done it above like minimal effort. It's probably most of you. And then I'll probably look for the ones where I can kind of see no effort whatsoever. I'm going to come out with take-home points from all of those, and I'm going to address them with you, and we're going to keep the grading fairly friendly for the semester, since that's kind of hard to do. I still don't have solutions to the exams. I'm going to post some homework assignments later on this evening for Chapter 7, and we can run through those. We can do those problems, and basically I'm going to try to bend over backwards and give you all the insight that you guys need, so long as I can hear the questions via Zoom. So I think we're about ready to switch over from YouTube Live to Zoom. Sierra, you got any customers?
So you we figured out the YouTube thing.
Oh, so they're chatting right now.
No,
Oh.
they need a YouTube like channel to then comment. So
I'm going to sign off, you guys, but I'll be back in touch over the Zoom thing, let's say in 5 minutes, and Sierra can explain this to me. Thanks, you guys.
So what's happening is we got it to so where you could chat But in order to chat now, I need to create a channel to join the chat.